Okay, welcome to lab here. So as I mentioned before, I think what we're going to do is we're going to continue lecturing since we're going to do the activity that's on Lewis structures and everything like that. So just want to make sure that we can kind of get through all the material so you'll be able to do that. So my anticipation is, and we'll talk more about it at the end, but my anticipation is that the activity that we were going to do today, which is the Lewis structure molecular model sort of activity, it will be due sometime next week. One of the days next week, probably Wednesday. Who knows? We'll see. But that'll give you time. That'll give us time, hopefully, to get through this here a little bit more, if not finish it. And then you'll be able to kind of do most of what's on that activity, and you'll be able to turn it in next week and kind of work on it and get some ask questions if you have questions and that type of stuff. So for today, in terms of the lab, there will be nothing that will be needed to be turned in or anything like that. And again, I'm assuming that the activity will be due sometime next week. Okay, so we started talking about Lewis structures and how to kind of draw Lewis structures for covalent compounds. So I went through the steps that you want to follow, and you really do want to kind of follow those steps. It usually will lead you to, I won't say 100% of the time, the perfect structure, but for most classes that you take in terms of chemistry, it usually will lead you to a pretty good structure in terms of a Lewis structure. So again, you want to organize all the atoms in a logical arrangement, typically, as we talked about there a second ago, that the least electronegative atom is in the center. And in a lot of cases, everything else is attached to it. We'll never find fluorine or hydrogen again in the center because fluorine is most electronegative and hydrogen can only have 2 electrons. The next almost most important thing than that is to count up the total number of valence electrons that you need to put in your picture. That number is really important, again, because your picture's got to have exactly to that number that many electrons in it. Again, you need to adjust the count if something has a charge. So if something has a positive charge, again, it means it lost electrons. So if it had a +1 charge, you would subtract off 1 electron from your total. If something had a negative charge, that meant that it gained electrons. So say it had a -2 charge, you would add 2 electrons to your total. Again, if you don't account for the charge, you will end up probably with a picture with the wrong number of electrons in there. Once you do that and you got the logical arrangement, you got your total number of electrons, it's at that point you want to make one single bond from the center guide to each of the outside ones. I personally use lines, so I make one line to each of the outside ones. You want to figure out how many electrons you just put into your picture and subtract off what's left over from your total. And those leftover electrons always go on the outside ones first, again, in pairs of electrons. So on your picture, dots, until all the outside ones have 8 electrons, except if it's hydrogen, then it should obviously only have 2 electrons and no dots. And if you filled up everybody on the outside one, like we did at the very end there, and you still have electrons that are left, they then go to the center guy and they are placed on as dots as well. So those are sort of the rules you want to follow. Once you've placed all your electrons, the last thing you want to do is make sure that everybody has met the octet rule. And if somebody has not met the octet rule, that is when you want to actually make a double bond to try to fix it. You want to kind of do all your double bond options. And if those still don't fix the problem, then you should go to a triple bond. So again, try not to double bond or triple bond right out of the gate. Not usually the right way. So let's take a look at another one here, example together, before I give you a few to do here. Let's go with, let's do HCN, for example. So HCN, if we count up the total number of valence electrons, hydrogen has 1, carbon has 4, nitrogen has 5, so that is 10 valence electrons. So in this particular one, our picture should have an absolute total of only 10 electrons. We want the least electronegative in the center. Hydrogen cannot be in the center. Between carbon and nitrogen, carbon is the least electronegative out of the 2. Carbon is further to the left on the periodic table. So that means the logical arrangement here would be carbon in the middle, nitrogen and hydrogen on the outside. At this point, what I want to do is make one single bond from our center carbon to our nitrogen and from our carbon to our hydrogen. At that point, each line represents 2 electrons, so that is 4 electrons I just put on there. That leaves me 6 electrons to go. I want to put the electrons on the outside atoms first in pairs. So I'm going to go to my hydrogen, and I am not going to put any dots. Again, hydrogen at this point is done. It has 2 electrons. Should never have dots around it or anything like that. That means I then want to go to my nitrogen and put my dots. So I got 2, 4, and 6 electrons. That takes care of those 6. I have now put on a grand total in this picture of 2, 4, 6, 8, 10 electrons. I am out of electrons at this point. I want to make sure that everybody has met the octet rule. So when I look at the hydrogen, it has 2 electrons right here. Make it darker. For my nitrogen, it has 2, 4, 6, 8 electrons, so it's good. But when I look at my carbon, it has only 4 electrons, 2 on each side. So it is short. So at this point, I need to fix that. I need to get carbon to 8 electrons. So you may say to yourself, can I just do this and just throw up some electrons there? And the answer would be that does give carbon 8. The problem, though, is if you just put dots down, you now have 14 electrons, which is too many. So you can't just put dots in there. So you can't just do that. So this is the part where we want to make a double bond. So we cannot double bond to hydrogen because hydrogen already has 2 electrons. So we can double bond to nitrogen. So can I put a double bond like that? And the answer to that question is it's a good start, but not correct, because if I double bond like that, I now have 12 electrons, too many. So when we're making a double bond, what we're going to actually do is we're going to take a pair of electrons from the place on the outside, and we're going to bring them in to make that double bond. And when we do that, we will end up with something that looks like this. And now when I look at my nitrogen, I have 2, 4, 6, 8 electrons, double bond counts. We got 2, 4 for double bond and our 4 non-bonding electrons, 8. Hydrogen still has 2, but when I look at my carbon, it got better. It's 2, 4, and 6 electrons. It is still short, which means since our double bond didn't fix the situation, we then need to move to a triple bond. So the same idea with our triple bond, we're going to take a pair of electrons and we're going to move it in to make our triple bond. And when we do that, we will end up with HC triple bond here and our nitrogen. Now looking at our nitrogen, we have 2, 4, 6, 8 electrons with our triple bond. Our hydrogen still has 2, which is this guy. But now our carbon has 2 for the hydrogen, 4, 6, and 8. And now has 8 electrons as well. Our total picture here still only has what we needed, 10 electrons. And everybody has 8 except for hydrogen that has 2. This would be our correct Lewis structure for HCN. Question on any of that there? So when you make a double bond, you want to take the electron pairs. You can either erase them and move them in to make that double bond. And again, if it doesn't fix it, then you want to go to a triple bond. Any questions on how I got to that picture there? Okay, so I'm going to give you some to give it a go and see, just to make sure. Why don't you do, let's do SO4 2 minus. Let's do, let's do, let's see, CH2O. Give that one a go. Why don't you do, let's do SO2. Why don't you do OF2? And why don't you do NO3 minus? All right, so take a few moments here and draw the proper Lewis structures for each of those. And again, least electronegative in the center, and follow sort of the same rule: single bond, fill up all the electrons, and then go on the outside and then to the center and dots, and then double bond or triple bond if necessary. Okay, so let's take a look and see how we're doing. Let's start with the first one. We'll go with SO4 2 minus. So again, really almost the most important thing, I think, is to make sure that you do get the right count in terms of valence electrons. So here, sulfur, which is group 6, we have 4 oxygens, which are also group 6. And again, here we do have a -2 charge. So the minus means that it gained electrons. The 2 is how many electrons it gained. So we do want to add 2 electrons to our total, again, for our charge that's present there. So that gives us a lot there, 24, 26, 32 valence electrons should be in there. Now, when we're comparing sulfur and oxygen, sulfur is the least electronegative, so it should be in the center. Also, just logic, in most cases, since there's only 1 sulfur and 4 oxygens, sulfur is probably in the middle. So we're going to do sulfur in the middle. We're going to do oxygen around. So again, at this point, what we're going to do is just simply put a single bond from the sulfur to each of the oxygens. And by doing that, at this point, I have now put 2, 4, 6, 8 electrons. That leaves me some more there. We'll go with 24. No, that what we got there? 24 to go, I think. So we got 24 electrons still to go. Those again are going to go on the outside in pairs until each of the outside ones have 8. Since we don't have hydrogen in here anywhere, we don't have to worry about that. So everybody's going to need 8 here. So that's going to be 2, 4, 6. That's going to fill that guy up. 8, 10, 12. That's going to fill that guy up. 14, 16, 18. That will fill that one up. We got 20, 22, and 24. That will fill that guy up. At this point, we have now put all 32 electrons on our picture. We want to make sure that everybody has 8 valence electrons when it's all said and done. So our oxygen, 2, 4, 6, 8. Oxygen on all of them are exactly the same. So they all have 8. When we go to our sulfur, it has 2, 4, 6, and 8. Everybody has 8 electrons. We have a grand total of 32 electrons. The last thing you should do whenever you draw anything that has a charge, like a polyatomic ion, you should always put parentheses around it. And you should put the charge on the outside. Just kind of make it all prettier, I guess. But you should always bracket it up and put the charge on the outside. Any questions on how I got to this structure here? Okay. So let's go to the next one, which is CH2O. So in this particular case, again, we're going to start with the valence electrons. So that is 4 for my carbon. I have 2 hydrogens, each at 1. And we have oxygen there, which is group 6. So that is 4 and 2 is 6. So that is 12 valence electrons. So let's talk about logical arrangement here. So hydrogen, as we talked about, can't really be in the center. So it's probably out of luck. So between carbon and oxygen here, carbon is further to the left on the periodic table, which means it's least electronegative. So probably a good structure would be carbon in the middle, oxygen on the outside, and hydrogen on the outside as well. All right, so we're going to follow our same sort of setup. We're going to do a single bond from the center to each of the outside guys. At that point, we have now put 6 electrons. That gives us 6 more to go. We're going to put them on outside in pairs. So we're going to go to the hydrogen and do the right thing and not put any dots on it. Again, it is full at this point. It has 2 electrons. So it should not take any more electrons at this point, either one of those hydrogens. So that really only leaves us one outside one to put these electrons on, and that is the oxygen. So we'll go in pairs. So 2, 4, and 6 at this point. At this point, we have now put 12 electrons on our picture. We want to make sure that everybody has 8. So again, our hydrogen has 2, so it's all good on both sides. Our oxygen has 2, 4, 6, and 8, so it's good. But when we come to our carbon, it has 2, 4, and 6 electrons, so it is not good. So it's at this point that we do need to make a double bond to try to fix it. In this case, we're going to take a pair of electrons from the oxygen, and we're going to bring them in again. To do that, remember that we do need to get rid of those electrons, otherwise we'll have too many. And if I do that, what I will end up with is a double bond here between the oxygen, and we will still have our 4 non-bonding electrons on the oxygen. And this should be now the correct structure here. Again, if we look at it, hydrogen still has 2, oxygen has 2, 4, 6, and 8. Carbon has 2, 4, 6, and 8 as well. So everybody has 8 electrons. We have still a grand total of only 12 electrons. So this would be the correct structure here. Question on that, how I got there? Okay. Continuing on, we're going to go to SO2. So we'll go here. SO2. Same idea, going to start with our valence electrons. So sulfur is 6. There's 2 oxygens, each has 6. So that is going to give us 18 valence electrons here when we do our math. Again, between sulfur and oxygen, sulfur is still going to be the least electronegative, so should be in the center. Oxygen on the outsides. I went left and right with the oxygen. You could go up and down. It really doesn't matter. Same approach here. We're going to do a single bond from the sulfur to the oxygen. That is 2 and 4 electrons. That gives us 14 more electrons to go. We're going to put them on the outside ones in pairs. So that's going to give us 2, 4, 6, 8, and that will fill up that oxygen. We got 10, 12, 14. That will fill up that oxygen there. So grand total now we have put on there 2, 4, 6, 8, 10, 12, 14, 16 electrons. We still have actually 2 more electrons to go. Everybody is full on the outside. Those last 2 electrons again go on as pairs on the center atom. So that will now be our total of 18 electrons. We want to make sure everybody is good in terms of electron configuration, our octet rule. So we got 2, 4, 6, 8 for the oxygen. Other oxygen is the same, 2, 4, 6, 8. Our sulfur, 2, 4, and 6 only. So here again, we do not have 8 on the sulfur, so we need to fix it by making a double bond. In this particular case, you could double bond either the oxygen on the left or the oxygen on the right. I'm going to go to the left here. Same approach. We're going to take a pair of electrons. We're going to bring those electrons in. And when we do that, we will end up with a double bond over here on the left. And a single bond over here on the right. And in terms of electrons, what that does is it still maintains its total 18 electrons. Oxygen on the left, 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8. Sulfur in the middle, 2, 4, 6, 8. Everybody now has 8 electrons, and we have a total of 18 electrons. This would be the correct Lewis structure. Now, you may ask yourself, I could have made the double bond from this oxygen, and you could have drawn a structure that looked like this. If you did that, you decided to double bond to the right oxygen, it would look something like this. And either one of these structures would be perfectly fine. these are actually two structures that are related to each other. These are what are known as resonance structures. And resonance structures basically occur like what we see here. It occurs when you do have sort of an option as to where you can sort of make the double bond. Sometimes a triple bond as well, but usually it's double bond related, but it can be triple. But we had an option here. We could have double bonded on the left like we did. We could have just as easily double bonded on the right. So these are really two structures that are related to each other, and they're known as resonance structures. And the truth is, these double bond electrons, for example, the double bond electrons that we got going on, those double bond electrons at some moment in time may be over here at the left, but they're sort of delocalized, which means they may also at some point kind of travel over to the right. And the real structure is probably somewhere between these two structures that we drew on the bottom. Because those double bond electrons are sort of moving. So at some instance, they may be on the oxygen on the left. Other cases, they may be over there at the oxygen on the right. So somewhere in between may fall sort of our real structure of it. So if you were asked just to draw the Lewis structure, you could have just drew either this guy here, or you could have drew this guy here. If you're asked to draw all the resonance structures, you would draw both of them. And we usually indicate resonance structures with these arrows that are kind of heading in both directions between them. So usually, again, it develops when you have multiple options as to where you could do that double bond. You could draw just as an equivalent structure by putting the double bond in the opposite location. Question on that there. Then that brought us to OF2. So let's take a look at that one. So oxygen is group 6. We got 2 fluorines, which are 7 each. That is, we got there 14, and 6 is 20 valence electrons. So in terms of oxygen and fluorine, obviously oxygen is the least electronegative. Fluorine will be on our outside. We're going to do, again, a single bond from the fluorine to the oxygens in there. That is 4 electrons that we use. That leaves us 16 to go. Again, going to go on the outside here. So 2, 4, 6. That fills up that guy. 8, 10, 12. That fills up that guy. I now have put on there 12 of those electrons. That still leaves me 4 electrons to go. Now that I filled up everybody on the outside, I go to the center, and it does go on as dots or pairs of electron. So that's 2 and 4, taking care of all that. We have now put on there hopefully 20 electrons. And if we put on 20 electrons there, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We want to make sure everybody has 8. So fluorine on the right, 2, 4, 6, 8. Fluorine on the left is identical, so also we'll have 8. Oxygen in the middle, 2, 4, 6, 8. Everybody has 8. We've used a grand total of our 20 electrons. We're good to go. That is the correct structure right there. So as you can hopefully be kind of seeing here, it's really important to follow those sort of steps because it's very, very common. People are so double bond, triple bond, I want to do that they always miss placing these non-bonding electrons on the center atom. So again, if you follow those steps where you fill up all the outside ones and then to the center with dots, you won't miss those, which is very common. Like I said, people sometimes will put extra bonds instead of where they should have dots on the central atom. So you definitely want to follow that path. Question on that particular one there. And that leaves us NO3 minus, I think. So let's take a look at that one. We got NO3 minus. So again, nitrogen is group 5. There's 3 oxygens, each at 6. Again, we have a minus charge, which means they gained electrons. So we're going to add 1 to that. That gives us 18, 19, 24 valence electrons in this case. Again, between nitrogen and oxygen, if you look at the periodic table, nitrogen is further to the left, which means it's the least electronegative. So we can put the nitrogen in the middle, oxygens around. Going to do a single bond from the nitrogen to each of the oxygens. That's going to give us 6 electrons we laid up there. That's going to give us 18 to go. That's going to go on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. So at this point, we have now put up 24 electrons. Looking at our structure, hopefully at this point you can see what's wrong with it. Oxygen is 2, 4, 6, 8. All the oxygens are the same. It is the nitrogen here at 2, 4, and 6. So it is short electrons. So we do need to make a double bond. And in this case, if you're looking at the structure, you can hopefully see that you have 3 options as to where you can make the double bond. You could actually make the double bond at any of those oxygens. So for the sake of my first structure here, I'm going to take the electrons from the top and I'm going to bring them in to make my double bond. And when I do that, I will end up with a structure that looks something like this. Double bond oxygen to the top. Again, we want to put a bracket around it because it has a charge and the charge on the outside. And if we look at it by doing that double bond, we have now fixed our problem. Nitrogen 2, 4, 6, 8, oxygen 2, 4, 6, 8, and our double bonded oxygen 2, 4, 6, and 8 electrons. Everybody has 8 electrons. We have still only a grand total of 24 electrons, which is what we're looking for. Question on that one there. So this as well, since we had options, we could have double bonded here. We could have double bonded here. We could actually draw 2 more resonance structures for this guy. So if we drew another resonance structure where we double bonded to the left, it would have looked like this. With now our single bond up on top. And we could have drew a third resonance structure where we could have double bonded on the right-hand side. And all 3 of these guys, again, are basically resonance structures of each other. And it's really because one structure alone really doesn't adequately sort of describe what is happening here. And again, sort of what is happening, just to give you an idea, as I mentioned earlier, those double bond electrons are essentially kind of moving around. So again, at some period of time, they may be over here on the left, making the double bond on the left. They maybe end up over here on the right, making that double bond, or up there on top, making that double bond. So again, these are all 3 equivalent structures. These are all 3 resonance structures of each other. And again, if you were asked just to draw the Lewis structure, you could have drew any one of those 3 structures. If you were asked to draw all the resonance structures, you should lay up all 3 of those structures right there. Question on how to draw Lewis structures in general here. Our resonance structures here that we're talking about. And we did see this one more. Let's take a look at one more together that we saw earlier, which was, excuse me, CO2. And just to show you again how we get to that structure that we saw earlier, carbon is 4, oxygen is 6, and there's 2 of them. So that is 12, and 4 is 16 valence electrons. So again, carbon here is least electronegative, further to the left. It would go in the center. And like we talked about, to get to the octet rule, sometimes we need more than just a single bond. So when we single bond here to 4 electrons, gives us 12 to go. Again, going to go on the outside here, 2, 4, 6, 8, 10, and 12 at that point. We have now put all 16 of our electrons here, and we want to make sure that everybody is good. Oxygen 2, 4, 6, 8 on both sides. Carbon 2 and 4. So not so good. So you can fix it by making a double bond, and you do have options here. So I'm going to double bond on the right-hand side and bring it in. When I do that, I will end up with something that looks like so. Double bonding in there. And at this point, you want to check to make sure it actually fixed the problem. So in terms of our oxygen on the right, 2, 4, 6, 8. Oxygen on the left, 2, 4, 6, 8. Carbon, though, 2, 4, 6. So it did get better, but it actually didn't fix the problem. So you really do have 2 options here. But usually what you would want to do in this case is you could think to yourself, I can make a triple bond by taking another pair of electrons in, and that is a possibility. But usually in terms of maybe a better structure that you'll end up with is you really kind of want to do your single bonds, and then when you try to fix it by doing a double bond, you kind of want to exhaust all your double bond possibilities. So in this particular case, since we have another oxygen on the other side that we can make a double bond, you probably want to do that first before, again, you leapfrog into triple bonding. So we would make a double bond on the other side here because we can, and we would do the same sort of move. We're going to bring those electrons in to do so. And what that's going to end up giving us is a double bond on both sides here. And when we do that, we are still maintaining the same number of electrons total, which is 16, but we have now fixed the problem that we need. We got 2, 4, 6, 8 for our oxygen on the left, 2, 4, 6, 8 for our oxygen on the right, and our carbon in the middle has 2, 4, 6, 8. So this really is sort of the right structure for CO2. It does look like this. Question on that one. Now, I will say that, you know, technically speaking, not necessarily 100% wrong to jump to a triple bond at that point, and you would end up with something like this. And technically speaking, it still fulfills everything. Everybody's got 8. You know, you got the right number of electrons. But what we don't talk about in this class is something you'll talk about in 1A. And what you would find in 1A is there's something known as formal charge that you can look at. And based on formal charge, this guy here probably would be the better structure than a triple bonded one. So there are really some more rules that come about that we don't necessarily get into in here, that you'll get into 1A, that helps you decide between a situation like that where you may go, hey, I could put maybe the bond some different way, you know, which way is a better structure than something else. So for our sake at this point, that's what I would suggest you do. You want to, again, single bond first out of the gate. If somebody does not meet the octet rule, you want a double bond to try to fix it. If it doesn't fix it and there's another double bond option, do that first. If you sort of exhausted all your double bond options and it's not going to fix it, then you should leapfrog into the triple bond. That's probably the best sort of course of action. And again, when you get into 1A, you'll talk about formal charge and and ways you could kind of use that to decide what might be a better structure than something else. Question on how to draw Lewis structures there. Obviously, you need to be able to draw Lewis structures, right? All right. So we're going to continue on-ish, I think, with the notes here somewhere where I want to pick up. All right. Put in a bunch of pages there. Let's see. Here we go. Now, as we talked about, there are some exceptions to the octet rule, and this is an exception to the octet rule. This is what is known as an expanded octet. So as I mentioned earlier, there are an exception to the octet rule, which is known as an expanded octet. And that basically means that there are some guys that can have more than 8 valence electrons. And that is an exception to the octet rule that you'll see a lot, especially in 1A, because there's a lot of geometries that go with those guys and stuff like that. So you talk about those guys a lot. But it usually happens on the periodic table right around our good friend sulfur. So if you look at sulfur on the periodic table, and then there's like chlorine, and there is phosphorus. So if you kind of go to the right, to the left of sulfur and down, those are the ones that have the ability to go above 8 electrons. And the reason for that is if you look at where sulfur is on the periodic table, that is in period number 3. And period number 3 on the periodic table means that the N value is 3, N equals 3. That means it's on the 3rd energy level. And if you think about what orbitals appear on the 3rd energy level, S orbitals are on the 3rd energy level, P orbitals are on the 3rd energy level. And if you remember from our talk about electron configuration, that is where we first start to see d orbitals appear. So on the 3rd energy level is where we first start to actually see the d orbitals appear. Now, even if these guys aren't technically using those d orbitals, they do have them available to basically house all the extra electrons. So those guys on sulfur, and we talk about sulfur because we're really talking about covalent bonding nonmetals. So sulfur is in the nonmetal region. So phosphorus, chlorine, left, right, and down, bromine, all those guys, they do have the ability to go more than 8 electrons because they do have those d orbitals available to them. So as you can see in this picture, if you follow our path to draw these things, you would end up with these pictures. So just to kind of show you how we get to this picture here, you would do the same approach. You would do your S, your F, and they counted that there's 34 electrons. So we would do a single bond, single bond, single bond, single bond, and that is 2, 4, 6, 8 electrons. So again, we have here, was that 26 more to go? So they would go on the outside, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have now put 24 electrons on the outside, plus my 8 electrons on the inside. That is 32 electrons. I still have actually 2 more to place. And those 2 more will be placed just like we normally do right there on the center atom in pairs. And that's how we get to the structure that we see here. Same approach if you followed here. Again, we just put those extra electrons on that center atom because it has the ability to do so because they possess d orbitals and they have places to put all those electrons. That also means, though, if you look at the periodic table and you look at the guys above it, sulfur, like carbon, nitrogen, oxygen, carbon, nitrogen, oxygen. These guys are on the 2nd period of the periodic table, which means N is equal to 2. And that means on the 2nd energy level, they have S orbitals available. They have P orbitals available. They do not have d orbitals available, which means anybody in period 2 should never, ever, ever go over 8 because they do not have the ability to go over 8. So anything that's in that second period, carbon, nitrogen, oxygen, fluorine, they should never go over 8 because they really do not have the ability to do so. Sulfur, left, right, and down does technically have the ability to go over 8, but for our class, you really shouldn't do it. Yeah, you probably should obey the octet rule, but in 1A, you'll go over a lot, but it does definitely have the ability to do that. And that may also answer a question if you ever looked at Lewis structures in your spare time when you're bored. I don't know why you would do that. But you will sometimes see when people draw SO4 like we did earlier, SO4 2-, and we came up with this structure here, which is a perfectly fine structure. For SO4 2-. And if you Google like sulfate or something like that, you will sometimes see it drawn like this. With 2 double bonds, which means that our sulfur in the middle, in this particular case, has 2, 4, 6, 8, 10, 12 electrons. And it's actually perfectly fine in that situation because it's sulfur. It has that ability to go over 8 because it has those d orbitals. And truth be told, again, a little bit outside of our class, you'll learn about it in 1A. This is actually the better structure here based on formal charge. But for our class, you probably shouldn't go over the 8. You should probably stick to the 8, but just realize that you can go over the 8. It is possible. And in certain cases, like the case here on the screen, really the one on the right is actually the better structure of the two based on formal charge. But that's, again, why you may sometimes see central atoms have more than 8, and it's definitely the sulfur left, right, and down because they have the ability to do so. Questions on that there? All right. So again, for our class, probably the one on the left would be the best structure. When you get to 1A, probably the one on the right would be definitely the best structure based on formal charge. All right. Probably for us, we'll probably obey the octet rule for our class most of the time. All right, so talk about that. Let's see here. We already talked about that, so I'm going to skip over some of the stuff that we talked about when we were drawing them. Here's our resonance structures that we talked about when we were drawing. Again, a reminder that basically a resonance structure is drawn when one structure by itself really doesn't adequately sort of describe the bonding that's happening. And again, usually it develops when you have more than one option in terms of laying up that double bond. And as you can see here, this is kind of the one we actually did earlier. These are the 3 resonance structures for nitrate. And really the only difference is we basically move the double bond from one oxygen to the next. And again, gives us basically an equivalent structure. So if you're asked to draw the resonance structures like we've been talking about, you would draw all 3 of these. If you're asked just to draw a Lewis structure for NO3-, you could draw any one of the 3 would be perfectly fine. Any questions on that there? Okay. And again, that arrow, like I mentioned earlier, is how we sort of distinguish that these 2 things are related to each other as resonance structures, that arrow that heads in kind of both directions. All right, so we talked about the expanded octet. We actually talked about this one as well, but again, just to remind you that the other sort of exception to the octet rule is that, excuse me, is that incomplete octet, which is what is sometimes referred to. And that is when we have guys that basically have less than 6 electrons. And like I said, typically boron, people oftentimes include aluminum and beryllium involved. But again, these guys, for the most part, will make more ionic type compounds. So we really don't come across it a lot with our incomplete octet. So our boron is sort of our example that we typically will see. And again, this is also sometimes referred to as an incomplete octet, where our last one was our expanded octet. And the last sort of exception is was sometimes referred to as a odd electron molecule. And that, much like it sounds like, is when we end up with an unpaired electron here. So instead of everybody gets pairs, we actually end up with one unpaired electron. And what we end up seeing is, let's see, which one would do, like NO, for example. NO, if you do just the valence electrons there, that is 5 for the oxygen or nitrogen and 6 for the oxygen. That's 11 electrons. So when you go to draw something like this, you got 2, 4, 6, 8, 10, and 11 electrons. You could try to fix it by making a double bond, and you'll end up with probably something that looks like this, where we have that unpaired electron there. Again, that is what is also sometimes referred to as free radicals. When you have those kind of one unpaired electron, happens a lot with chlorine chemistry, and typically those are super reactive because they have kind of one unpaired electron. So NO is an example of that, where that happens. So those are sort of 3 common exceptions to the octet rule: expanded octet more than 8, incomplete octet less than 8, and an odd number of electrons, which means not all paired up electrons, one unpaired electrons. For our class, we will obey the octet rule for everything. So for us, you just need to know the exceptions, what the 3 exceptions are: expanded octet, incomplete octet, odd number of electrons. But when you're going to be asked to draw Lewis structures for us in here, you'll be asked to basically draw it obeying the octet rule. Just know in your head that there are exceptions. And I will say, like I mentioned a couple of times, that when you get to 1A, you're going to see a lot of that expanded octet is a very common exception. Which of these can exhibit resonance? We drew this guy earlier, and this is the one that can exhibit resonance structure. Again, we could have drew the double bond left or right, so that's one of the ones we drew earlier. N2, as we also drew earlier, ends up with a triple bond, and there's no real chance of resonance structure there. And if we did carbon tetrachloride, carbon is 4. There's 4 chlorines, that's 7. That's 28 electrons, plus 4 is 32 electrons. Carbon is less electronegative than chlorine, so we would put the carbon in the middle, chlorine on the outside. 1 single bond to everybody. That is 8 electrons that have been used, gives us 24 to go on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. That is 32 electrons. Everybody is perfectly good and happy. There would be no need to double bond or anything like that. So good structure there, good structure here. This would be the only one that will probably do any type of resonance structure where you have options in terms of double bonding. Question on that particular one there. Okay. We talked about drawing multiple bonds. All right. Any questions on drawing Lewis structures or anything like that? Okay, so what we're going to talk about now is geometry or molecular geometry, which is known as VSEPR. And that's, again, valence shell electron pair repulsion model, which is why they abbreviated it. And we can use our Lewis structures to predict the geometry. And there's going to be 2 types of geometry we're going to talk about. One is what is sometimes referred to as the electron pair geometry. I think your book may call it electron group geometry. And one is referred to as the molecular geometry, or that is sometimes referred to as the shape. So these are 2 sort of different names. One name describes how the electrons are arranged around the central atom, and that is non-bonding electrons, bonding electrons, doesn't matter, just in 3-dimensional space, how those electrons are arranged. The other one, which is the molecular geometry or the shape, is what the overall molecule as a whole its shape is. And in certain cases, as we will see, these names will be exactly the same name. And in certain cases, these names will be different names. And one really important thing to keep in mind when you're doing geometry, and only when you're doing geometry, is if you have a double bond or a triple bond, when you are doing geometry, that double bond or triple bond counts as only one electron pair and one bond. So if you draw a Lewis structure, you got a double bond, triple bond happening. When you go around to count, which is an important sort of aspect of doing the geometry part of it, you count your double bond or triple bond as one electron pair and also one bond. So when we look at things, whoops, come back here. As I mentioned, they're all considered basically a single electron pair and a single bond. So that makes it really sort of easy when you're counting double bond, triple bonds, one of each of those things. And that's ultimately when we do sort of geometry, what we're looking for is we always are interested in the center atom. The center atom is always the important guy. And we always want to look at the center atom. And those really are the two things you want to look at. How many electron pairs there are. Doesn't matter if they're dots, doesn't matter if they're lines, total number of electron pairs. Again, the only thing that matters, double bond or triple bond counts as only one. And you also want to look at how many bonds there are around the central atom. So usually when you go to sort of memorize the geometry part, that's what you want to look at. Center atom, always the important one when you're doing geometry. How many electron pairs there are, dots, lines, and how many bonds there are, which are the lines, basically, when you draw your things. Now, before we get to sort of the geometry that they're going to basically talk about here, let's talk about the easiest geometry that there is. And the easiest geometry that there is a diatomic molecule. So when you have a diatomic molecule, there is no center atom because there's only two atoms. So if you have F2, you basically only have two atoms there. So whenever you have two atoms, the only way you could basically arrange two things is within a straight line, at the end of a straight line, basically. So the geometry of anything that is a diatomic will be linear. And again, there's really only one geometry, which is linear, because there is no central atom. So F2 would be linear. Doesn't matter if it's a single bond, double bond. O2 would be linear. Doesn't matter if it's the same element or different elements. The geometry of this guy would be linear. Doesn't matter if it's a triple bond happening. This guy will be linear. So definitely the easiest out of all of them to determine the geometry is diatomic. So if you draw something that's diatomic, that's all you want to do is just put linear there for the geometry, because don't even think about it. Even if it's two different guys, two same, single, double, triple, always going to be linear as we go through it here. So let's talk about what happens when we have three or more atoms involved. We want to talk about the geometry that goes with it. And here is the electron pair arrangement or electron group arrangement name. So the first one that we're looking at, if we look at our central atom here, this is our central atom. It has one electron pair, two electron pairs. So something with two electron pairs, the electron pair geometry name is linear. That means that those electrons have basically moved as far apart as they can from each other, and it will have a bond angle of 180 degrees, basically a straight line there, 180 degrees apart from each other. And that is because ultimately the idea here is these are electrons and these are electrons, and they're both negatively charged. And what we know about things that are negatively charged, they don't like to be around other things that are negatively charged. So they're going to try to get as far apart as possible from each other. And in the case of two electron pairs, that is linear for the electron pair geometry. When we have 3 electron pairs, so we go to our central atom, 1 electron pair, 2 electron pairs, and 3 electron pairs. 3 electron pairs, the electron pair geometry name is trigonal planar. Sometimes people call this triangular. It has a bond angle of 120 degrees, and that is because it makes pretty much a equilateral triangle going on there. Yeah, so it makes a nice little triangle type shape, and that is what is known as trigonal planar electron pair geometry name. When you have 4 electron pairs, again around the central atom, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, that has a name of tetrahedral, and it has a bond angle of 109.5, almost like a pyramid type shape on the bottom, kind of makes a triangle on each of the faces of it, and it has that bond angle of 109.5. So these 3 names are the electron pair geometry, or the electron group arrangement. So this is the electron pair geometry, I usually call it. And again, doesn't matter if it's single bond, double bond, triple bond, everybody counts as 1 electron pair around the central atom. Any questions on that there? All right. Now, when we look at linear, that's the one we just talked about. Here we go. Let's do this one here. Let's look at this one. All right. So if we look at this example here, which is CO2, and we go to the central atom, which is the important one, it has 2 electron pairs. Double bond counts as only 1 on each side. So it has 2 electron pairs. Also has 2 bonds, 1 on each side. Again, double bond counts as 2 electron pairs and 2 bonds. So something with 2 electron pairs, as we talked about in terms of electron pair geometry, is going to be linear. The molecular geometry will also end up being linear as well. So that is the second name, which is basically the shape of the molecule. So 2 electron pairs, 2 bonds will give you linear for the electron pair geometry, and also linear for the molecular geometry are the shape of it. And CO2 is an example here. Again, bond angle 180 degrees. The bond angle is really tied to the electron group name there. As you can see here, we have that 180 degree bond angle, sort of our space field model here. This is our carbon. These are our oxygens. And again, you can see it pretty much makes a nice linear line that's happening there in that particular molecule. The next geometry is when we have 3 electron pairs and 3 bonds. An example of that is our BF3, which is our incomplete octet. If we go to our boron, which is right here, has 1 electron pair, 2 electron pairs, 3 electron pairs. Also has 1, 2, and 3 bonds. So something with 3 electron pairs and 3 bonds is known as trigonal planar for the electron pair geometry, and also trigonal planar for the molecular geometry, are the shape. And again, that is because, as you can see here, essentially makes a nice little triangle that's happening. And the bond angle, again, 120 degrees difference. So 3 electron pairs, 3 bonds, trigonal planar for both the electron pair geometry and the molecular geometry name. The next geometry is one where we have 3 electron pairs, but only 2 bonds. So if we look at the sulfur here, it has 1 electron pair, 2 electron pairs, and again, double bond only counts as 1. So that is 3 electron pairs and has 1 bond and 2 bonds. So 3 electron pairs, but 2 bonds. 3 electron pairs, it is trigonal planar still, the geometry of those electrons. Oops, come back. And that is because if we look at those electrons, it basically still makes that triangle type shape. But because we're missing that 3rd bond, that allows these oxygens to basically spread out a little bit further than they normally would. And it gives us a molecular geometry name of bent. Most people also go with angular on that one. So most people will call this angular as well, or bent angular. And what happens to the bond angle, as you can see, is unlike our 120 that we see with trigonal planar, our 3 electron pairs, 3 bonds, because we're missing that 3rd bond, it allows those guys to move a little bit further, those oxygens away from each other, and we actually get a smaller bond angle than 120 degrees. We get less than 120 degrees, 117 degrees in this case. And again, that's because it doesn't have that 3rd bond to lock it into place, so it's able to bend a little bit more, and the overall name basically changes the shape of it. So just to kind of show you here the 2 examples that we just looked at, here with our 3 electron pairs and 3 bonds, basically when we look at the central atom, they're all bonding electrons that are there. And because they're all bonding electrons, both of these names will be the same. So whenever you draw a Lewis structure and your center atom does not have any dots, the electron pair geometry and the molecular geometry will be the same name. It is only when we introduce, like we just did here, non-bonding electrons on the central atom that we get some interaction that is not so friendly. We have non-bonding electrons and bonding electrons, and they're able to basically move a little bit more in terms of its geometry. And that's where we start to get different names here. And I'm going to shut up now because I talked way too much today and take a nap. So here's the deal. We're just going to continue lecturing on this, obviously, on Monday. At this point, you could do a good amount of the activity. So if you want to get a start on it, you should be able to at least draw the Lewis structures and that type of stuff. So you could get a pretty good jump on it. It will be due probably Wednesday of next week. So again, if you want to kind of work on it, you can, and you should be able to at least do a little bit of it at that point. We'll finish up talking about geometry. We'll also finish up talking about molecular polarity on Monday as well. VSEPR model is basically the geometry of a molecule, sort of what it looks like in 3-dimensional space. A stick model is basically, for lack of a better word, like a model kit, like you put sticks together and they're balls and sticks, and you kind of build the molecule on it and stuff like that. So a stick model is kind of this guy right here. Kind of looks like this. What's in that little blue picture there. While a space-filled model was that one where it was like all circles, blobs of circles together, is sometimes referred to as space-filled model. So VSEPR is more the geometry aspect of it. A ball and stick model is more of a representation of the geometry. All right. Other than that, have a good weekend. Thanks for listening, and we'll see you on Monday. Yes. Make sure you put here if you haven't done so.